it is taking so long time. Okay, so the first part, if you have any confusion, because I forgot to start recording, but this part I have now our meeting is recorded. So non-holonomic system, I'll explain how this comes arise, and we need another method, technique, mathematical technique, which is called Lagrange multipliers method. Today probably I'll talk about this mathematical technique part, and in next class I'll use that to deal with non-holonomic system. So where the difficulties come, so we use Hamilton's principle. Hamilton's principle we use for the holonomic situation. And if you remember in the derivation we had, when delta S equal to 0, we had T1 to, so we have dt of del L del Q I dot minus del L del Q I, and then this quantity delta Q and then dt. Now this Qi all are generalized coordinate and independent. In this you have a holonomic constant, so I have eliminated, I can well define my generalized coordinate, and all these Q's are independent, and from there, if they are all independent, then I can get the Euler-Lagrangian equation ddt of del L del Qi dot minus del L del Qi equal to 0. If these are not independent, then I cannot compare their coefficient to 0 inside the integration. Okay, so that we cannot do. So now when we have non-holonomic constraints, then we will not able to find all independent conditions. So that will create the problem. So what we'll do, we'll see how to deal with this situation. So non-holonomic constant in generally has a time dependence, that I said, that velocity dependent. So that constant is generally, suppose I have a constant like this, generally expressed in this. So non-holonomic constant, I'll explain. Is if you have L number of constant, then it can be maybe first I'll write 1. So AK dqk plus AT dt to 0, because it is velocity time dependent, so time dependent. So k is the number of q, generalized coordinate, if possible. So suppose we are assuming that it is possible that we have n number of generalized, if it is n degrees of freedom, so we can expect that there will be, we can expect that will be better language, will be n number of such constants. But we cannot eliminate all those because of this. So this is only one constant. So now if you have many, suppose we have m number of such constant, where m less than n, it should be less than degrees of freedom. So what I can write, I can put all together, so this I can put a 1 and 1. Then second constant I can write 2k dqk plus a 2t dt equal to 0. Third I can write a 3k dqk plus a only coefficient which can depend also on the q, can be changing, 3t dt equal to 0. This is the style of writing. So I have L number of, so I can write, combine this and make a compact notation. So sum over, this is sum over k. Remember when I have this, I forgot, but I should write sum over k, this k and this k. Like it is like ax dx plus ay dy at dt equal to 0. Once in 2 dimension, this is one style of writing. Okay, so this summation, this means summation. So I can write, if you have m number of such constants, so I can write this equation sum over k and a lk. Now I use l dqk plus a lt dt equal to 0, sum over k 1 to n, and L equal to 1 to 3 to m. Okay. So suppose you have m number of non-holonomic constant, a system with degrees of freedom n, then in general non-holonomic constants I can express like this. Okay. So this equation, this equation, let me write this equation as equation 1. So this equation is very important, and you have to understand these coefficients q lk and q a lk and a lt. I hope everybody has understood that L equal to 1, I'll get this first equation. L equal to 2, I'll get this equation. L equal to 3, I'll get this. Similarly, n such equation. So m such equation will be there, and this every equation is summed over the number of possible number of generalized coordinates. Okay. Okay. So this equation 1 is important for us, and this coefficient a lk and a lt, they can also depend on q, I and t. Okay, in general. So this is most general. So now if we construct the variation of the path delta s equal to 0, that there will be many paths. So in which path delta s equal to 0, which is subjected my variation. So this is we call the variation of the path. The path subjected to constraint 1, because this equation. So if it is possible to consider the variation of path subject to this condition, then we can put delta s equal to 0 and find equation of motion. But it is in most general case, it is only possible to consider the variation of path subject to this when this equation is integrable. So variation subject to this condition is possible only when this constant equation 1 is integrable. That means you can integrate and remove the time dependent. So if it is integrable, then it will go to the holonomic constant. Okay. So that is why I said, even though it is I am discussing a method for non-holonomic cases, but if you use Hamilton's principle, then effectively it becomes a holonomic case. But the method can well valid if you can do with a non-holonomic system. Okay, so this is the drawbacks of this. You can read Griffith book. Goldstein book. Sorry, Griffith is called. Goldstein book for this part. Okay, so if only the variation of the path subjected to this condition is possible only when this equation is integrable. That means your non-holonomic constant will become holonomic. So that will not serve the purpose if we want to do the holonomic. So if I want to do really non-holonomic, this way you can study the holonomic case also. But if you really want to study non-holonomic, then variational principle you have to apply variational principle. That means that variational principle you consider for Hamilton's principle, that variational principle, keeping that this constant is another possibility is that introduce the virtual displacement. So we consider the real motion, variation of path constructed from the by considering a virtual displacement. What is the virtual displacement? It is instantaneous, that delta t or dt equal to 0. So if I consider the variation of path due to virtual displacement, then this equation, this delta t will be 0, and we have this equation only, and we can do the variational principle, Hamilton's principle. I think you read it fast. If you will have doubts and then ask me, then it will be clear. But to do this, so the variational principle using virtual displacement, that means to use this constant condition without this term, which is also kind of possible when this equation is integrable. But if this is not integrable, then also we can do similar thing by considering virtual displacement. Okay. So this you read. Up to this, I'll not tell anything extra on today on this. To next class you can ask, then we'll tell. So you can now have a variational principle with ALK dqk or del qk equal to 0, this and considering the virtual displacement. So variational principle of this with consistent with this constant condition, and we consider virtual displacement. So what is the physics going on when we later after finishing this we'll tell you, and this for L equal to 1, 2, 3 to m. Okay. And then we'll consider this S equal to T initial to T final L qi dot T dt, and now subjected to not equation 1 but now equation 2. Okay. Because I bring the virtual displacement, and virtual displacement means this instantaneous displacement delta t equal to 0. So this so delta q when delta t equal to 0, mathematically you can consider call it virtual displacement. Okay. Okay. So now to consider this, so in presence of this condition, I have to extremize this. So mathematically problem is that we have to extremize S in presence of this condition 2, ALK delta QK equal to 0. So this is the now mathematical problem, and this mathematical problem can be done by a method which is called Lagrange multipliers method. This I'll talk about in little bit of detail. So let me in today's class, in rest remaining 17 minutes, we'll discuss this method. So suppose I have this method you will not get in Goldstein book, you have to get from other book. One book I told you in the beginning, that Indian book Takwale and Puranik. So that book has details of this method. So you can get this method from many books, but details as I will be teaching you will not get. This is very important methods you will be using many places if you do MSc in physics. For example, statistical mechanics, it will be frequently used. But anyhow, so please try to learn. Suppose I have a function. I am just now away from my classical mechanics. We are doing some mathematics. I have a function xyz equal to 0. I want to find a extremized condition when this function will be extremum. So function will be extremum when delta f equal to 0, right? So delta f equal to 0 implies that del f del x dx, del f del y dy plus del f del z dz equal to 0. Okay, so but my x, y, z are independent variables, right? X, y, z are independent variable. So if they are independent variable, then this term cannot cancel with this term or this term. So all terms separately should be 0. So the extremization condition for f x y z equal to 0 will be del f del x equal to 0, del f del y equal to 0, del f del z equal to 0. So this extremization of this function will be this. Okay, so this is case 1. Now case 2. Now problem 2, I am saying the extremize this function f x y z equal to 0 under extremize this function. This is not, this is a function, so not 0. This function, extremize this function when g1 of xyz equal to 0. That means the presence of a constraint. Now xyz, I am asking that extremize this function when g1 of this equal to 0 under a constant condition. So if you have to do again this del equal to 0 when g1 xyz equal to 0. But now I will not get these conditions because now x, y, z are not independent. X, y, z are dependent through this relation because this is a constant. I don't know how to eliminate x in terms of y, y in terms of z, or x in terms of z, but I know that they are related. The relation, explicit relation I cannot find, but they are related. So this again I will write. So this you can write del f del x dx plus del f del y dy plus del f del z dz equal to 0 because del f equal to 0. But now I cannot say del f del x equal to 0 because x, y, z are not independent. So this Lagrange method of multipliers now suggests, okay, so now you demand that not this, demand that df plus lambda dg1 equal to 0, where dg1 will be del g1 del x dx, so on, right? Del g1 gy and so on. Then this is the multipliers. This is Lagrange multipliers. So to tackle with that, when you have presence of a constraint, how to extremize, then that we need that, okay, you put a condition like this. So what you will have, if you put this condition, then del f del x plus lambda del g1 del x times dx plus del f del y lambda times del g1 del y dy plus del f del z plus lambda del g1 del z dz equal to 0. Now we have now not 3 variable. Now we have 4 variable. How 4 variable? X, Y, Z and lambda. Lambda is the multiplier. It is also a parameter kind of thing. So instead of x, y, z, I have lambda. So four unknown variables and one condition, g1 equal to 0. This is a condition. So I can expect there are 4 variables I can expect one condition. So I can expect three of them, three of these four, three of them will be independent. Okay. Three of them, so I can have a x, y, z are independent, and immediately I can write that my extremization condition will be lambda d g1 dx equal to 0 del f del y plus lambda d g1 dy equal to 0 and del f del z plus lambda d g1 dy equal to 0. So this method says that you can get this condition for extremization, but lambda we put by hand in our theory, right? So if we put lambda by hand in our theory, then we should eliminate this lambda also, right? So there are three conditions. So equation, so one equation, any one equation you use to lambda should be eliminated. So lambda will be del f del x minus del g1 del x. Okay. And then you substitute lambda in these two conditions. Okay. That will give you the condition for extremization. Okay. So this method is called Lagrange methods of multipliers. I introduce a new variable to make them x, y, z are independent, because now I am matching, there are four variables, one condition, three of them should be independent. I am assuming x, y, z are independent. Then I get three equations. One equation will be used to eliminate this lambda, because lambda was not there in our theory. Lambda had a role to do this mathematics. Okay. So this is now you can very easily see. Okay, if I case 3, if I say that extremize f x y z when g1 x y z equal to 0, g2 x y z equal to 0. Two condition I put. See, we have to deal with this L number of conditions, that we have to deal, and I have to extremize this S. So that mathematics we are developing, and through this multipliers method. So immediately I can say, okay, df plus lambda 1 dg1 g1 plus lambda 2 dg2 should be 0. This will be my condition. Then there will be 5 variables x, y, z, lambda 1, lambda 2, and 2 conditions. So again 3 of them will be independent. So I assume x, y, z are independent. So again I will get the condition del f del x plus lambda 1 del f del g1 x plus lambda 2 del g2 del x equal to 0. Similarly del f del y plus lambda 1 del g1 del y plus lambda 2 del g2 del y equal to 0, and similarly for z. So let me write is needed. See, now what happened, I have 3 equations, but I have 2 variable which I put by hand. It was not there in my theory. My question was that you have to extremize this function in presence of this, where lambda was there. So I bring lambda for each constraint. Now you have to eliminate this lambda 1 and lambda 2 using 2 of this equation. Suppose first 2 equation I use to eliminate lambda 1 and lambda 2. See, we don't need to find lambda 1, lambda 2, we just eliminate. So we eliminate then final equation, we substitute lambda 1 and lambda 2, and then we get the condition for extremization. Okay. So this is the Lagrange multipliers method. I'll give you one. I'll solve one problem using this method. I'll tell you that. Then you will be able to understand this method well. Suppose I said this is a school problem, school children problem, that show that among the rectangles of with fixed perimeter square has maximum area. You understand the problem. I said that okay, you can have this rectangle, you can have this rectangle, you can have a square out of this. All rectangles have the fixed perimeter. That means if A is the side, B is the side length and breadth, then A plus B equal to constant, fixed. A plus B is half of the perimeter, so it is perimeter is 2C constant. Now you have to prove that among such rectangles, I can have infinitely many rectangles, but square will have maximum area. So area is your rectangle area is AB. So problem mathematically in our multipliers language, you have to maximize this when A plus B equal to C condition. So you have to extremize this in this condition. So let us do, and you can find whether this you can find. So dA you can calculate dA plus lambda this condition lambda this dA plus dB will be 0. So dA will be A dB plus B dA plus lambda dA plus lambda dB equal to 0 in our multipliers method. So A plus lambda dB, this and this and this, plus B plus lambda dA equal to 0. Now you can take A and B are independent because I have introduced lambda. So immediately I get B plus lambda equal to 0, A plus lambda equal to 0. That means now if you eliminate lambda, lambda equal to minus B. So A minus B equal to 0. So A equal to B. So A equal to B means square. So there are many problems even in the school level problems you can solve by this method. So please learn this method in JEST or GATE exam. I have never seen, but I have seen JEST exam problems in basis of multipliers method. But these problems are generally difficult in that sense. But if you have learned whatever I taught in last half an hour or so in this multipliers method, this is very clear teaching of this Lagrange multipliers method. Nowhere you will get in this much details, but try to solve some school problems where the maximization, minimization subjected to some condition. Under this condition, so another problem is that you can consider that you have learned quantum mechanics that if you have a box potential of length, say box of A, B and C, length, breadth and height. So you calculate the ground state energy, quantum mechanics, ground state energy of a box, three-dimensional box with side ABC. Show that this ground state energy will be minimum And this is for fixed volume. So this box with a fixed volume. So ABC is some constant K, and then you find that show that ground state energy will be minimum when this for a cube. That means you have to prove that it will be minimum only when A, B, C by A equal to B equal to C by this multipliers method. So you try to solve this energy level. If you don't remember the energy levels is basically like this box problem, right? So so energy levels are some I forgot, n square pi square h square 2m L square. Okay, so ground state energy ground n equal to 1. So energy levels will be pi square h square by 2m, then 1 over a square plus 1 over b square plus 1 over c square. So minimize this subjected to a b c equal to constant. So you do this problem and try to find, see that it will be for cube, it will be minimum. See, sometimes it will be minimum, sometimes it will be condition is same, extremization. Okay, so it is exactly 11. I'll stop here unless you have quick question on the Lagrange multipliers method. Okay.
सर अगर
हाँ.
जैसे हमारे पास अभी एक एफ फंक्शन था एक्स वाई जेड का, और हमारे पास दो कंस्ट्रेंट्स थे, तब तो हमने कर लिया ऐसा, क्योंकि तीन इक्वेशंस बन गए थे, तो हम लैम्डा वन लैम्डा टू दो इक्वेशंस एलिमिनेट करके थर्ड में पुट कर देते हैं। अगर तीन होता है तो फिर कोई और मेथड यूज करते हैं?
नहीं, अगर तीन नहीं, बट इफ
अगर
यू
तीन
हैव
कंस्ट्रेंट हो गया तो हमें फिर लैम्डा थ्री इंट्रोड्यूस करना पड़ेगा, फिर हम उसको एलिमिनेट नहीं कर, मतलब एलिमिनेट तो कर लेंगे कि तीन इक्वेशंस उधर से, लेकिन फिर उसको किस में पुट करके हम लोग इक्वेशन बनाएंगे?
नहीं, तीन में आपको जरूरी नहीं है ना. सो इफ यू हैव f x y z and if you have three condition, that means your x y z all are fixed, so f will have only one value. So don't, no question of extremization. If you have three condition, then x y z all will have a only fixed value.
ओके सर, फिर ऐसे तो उसके ऊपर के भी सारे वैल्यूज के लिए, मतलब अगर इससे दो से ज्यादा
नहीं
कोई भी कंस्ट्रेंट्स होंगे
नहीं,
तो
तो number of
वैल्यूज होगा।
constants should be less than number of variables.
ओके सर।
That I wrote na, n m is less than n in our discussion earlier, this discussion of non-holonomic case. This L up to m and m is less than m is L and m should be m should be less than n. This has to be, otherwise it will be fixed. If you have number of variables and number of constants are same, then there is no freedom left. So all the values are fixed and no question of minimum maximum. It will be only one value. Okay. Any other question? Hello. So let me, if you don't have questions, so let me close the class.